Hello, you're welcome to Medical Sciences by Naphtali Muhumuza, and we always at your service. Always remember to subscribe, those who haven't subscribed, and like, then share your comment below the comment section so that we can always see how to improve this service. And today we want to talk about, in the previous video we have finished glycolysis, and you have seen the end product of glycolysis. So if you haven't watched the video about glycolysis, before you watch this, first see the video on glycolysis, whereby the end product of glycolysis is pyruvate in the presence of aerobic and lactate in anaerobic condition. So now we want to see the fate of pyruvate, which was formed as a product of glycolysis. How do we use glycolysis? How do we use this pyruvate to get energy? And we have seen there are two steps, that when we form pyruvate as an end product in glycolysis, we shall see that this pyruvate, which is formed a 3-carbon sugar, pyruvate which is a 3-carbon sugar, and we formed 2 of them, they are converted to acetyl-CoA. Acetyl coenzyme A, and still we form 2 molecules of acetyl coenzyme A, and this acetyl coenzyme A is a 2-carbon sugar. So meaning, converting a 3-carbon sugar to a 2-carbon sugar, we are doing a process known as decarboxylation, whereby we are removing the carbon. So we see there is release of carbon in the form of carbon dioxide, and there are 2 molecules of them. Then we are going to oxidize. There is an oxidation reaction, whereby NAD plus is converted to reduced NAD. And whenever I see NAD, I think of a dehydrogenase enzyme. And these dehydrogenases, as I told you at first, that we are name them according to the substrate they are catalyzing. So I'm going to see an enzyme known as pyruvate dehydrogenase enzyme. Or you can call it pyruvate decarboxylase, because it is removing the carbon dioxide, 2 carbon dioxide molecule. Here we form 2 NAD, because we use the 2, because everything is 2, leading to formation of acetyl-CoA, which is a 2-carbon. And this one bridges, it is a transition step. Why? Because it's the one that bridges glycolysis with the Krebs cycle. And where does it occur? This transition step occurs in the mitochondrial matrix. Occurs in the mitochondrial matrix, and it occurs in the presence of oxygen. Oxygen is required in this transition step. So here the major product of this transition step, we see production of 2 NADs, and these 2 NADs, I told you that when it is shuttled in electron transport chain, this 1 molecule of NAD produces 3 ATP molecules. So since we are producing 2 NADH, we shall get 3 times 2, and we shall get 6 ATPs produced during transition step. That is when shuttled in electron transport chain in aerobic conditions. Then the acetyl formed is always the precursor of Krebs cycle. So this one leads us into Krebs cycle, which we call tricarboxylic cycle, because it contains 3 carbon sugars. And it is known also as citrate cycle, because the precursor is citrate, the first substrate formed, the product formed. So this Krebs cycle, we must know what is it, we must know where does it occur, we must know when, and we have to know how and why does it occur. As I told you that in the biochemistry pathways, we always have to answer these 5 questions of life. And these questions of life, you should always also ask them in your life to check where you are going, or if you're on the right track. So what is the Krebs cycle? Krebs cycle is a series of chemical reaction whereby acetyl-CoA, coenzyme A, acetyl coenzyme A is converted to water, carbon dioxide with the release of ATP. That is Krebs cycle, and it occurs in the mitochondrial matrix. Whereby in the mitochondrial matrix, we see in case there is low ATP and the body needs more energy, it is the one that triggers Krebs. Then also increased levels of oxaloacetate can increase this. Then how does it occur is what we are going to answer. Then we shall end up answering also why does it, the body transports glycolysis, performs glycolysis. And there is a mnemonic we normally use to remember this cycle, whereby this mnemonic says citrate is Krebs starting substrate for making oxaloacetate. This is the mnemonic we are using. We can use this mnemonic to always remember Krebs cycle, whereby citrate stands for, it is remains citrate, is for isocitrate. Krebs is alpha ketoglutarate. Starting is succinyl-CoA, coenzyme A. Substrate is for succinate or succinate. Then 4 is fumarate. Then making is malate. Then oxaloacetate remains the same. So this is the mnemonic we can always use to remember the steps in the Krebs cycle, whereby citrate is Krebs starting substrate for making oxaloacetate. Whereby I know that citrate, when I have citrate, we have 2 molecules of acetyl-CoA, coenzyme A, which come and combine with a 4-carbon sugar that is oxaloacetate, we form citrate. And this citrate undergoes isomerization to form isocitrate. And this isocitrate is converted to alpha ketoglutarate. And this alpha ketoglutarate is again converted to succinyl-CoA. Then succinyl-CoA is converted to succinate. Then the succinate is hydrolyzed, it is converted to fumarate. Then fumarate is converted to malate. Then malate gives back to oxaloacetate. That's why we say citrate is Krebs starting substrate for making oxaloacetate, occurring in the mitochondrial matrix. And step number 1 in the Krebs cycle, we see it is a ligase. We need a ligase enzyme known as citrate synthase. Citrate synthase is the one that catalyzes the joining, whereby acetyl-CoA combines with oxaloacetate. This is a 4-carbon sugar. This is a 2-carbon sugar. We form citrate, which is a 6-carbon sugar, in the presence of citrate synthase. And after forming citrate, we see an enzyme known as aconitase catalyzing an isomerism reaction, whereby there is intramolecular arrangement of citrate to form citrate by an enzyme known as aconitase, which is always inhibited by fluoroacetate. Fluoroacetate inhibits aconitase. Then the isocitrate, which is formed here, it is oxidized to alpha ketoglutarate. And this isocitrate is a 6-carbon sugar, and we are forming a 5-carbon compound, meaning we are using a carbon molecule. And this carbon molecule is lost by decarboxylation reaction, whereby we are losing 2 molecules of carbon dioxide. That is decarboxylation. And here we are forming NADH, whereby 2 NAD plus react to form 2 NADH. And whenever I say NAD, I think of the dehydrogenase enzyme. And this dehydrogenase enzyme is known as isocitrate dehydrogenase. Isocitrate dehydrogenase enzyme is the one that catalyzes the oxidation of isocitrate to alpha ketoglutarate, which is a 5-carbon sugar, with the loss of 2 carbon dioxide molecules. Because here every compound there are 2. We have 2 molecules because we use the 2 molecules of acetyl-CoA. Here everything is 2. That's why we multiply by 2. Everything is 2. So this one leads to formation of alpha ketoglutarate, and this alpha ketoglutarate undergoes the further decarboxylation to form a 4-carbon compound. And this 4-carbon compound is succinyl-CoA, whereby we need addition of the coenzyme A. Coenzyme A is added, coupled with decarboxylation. There is loss of 2 carbon dioxide molecules, whereby we have NAD plus being reduced to NAD, forming reduced NAD. And still, whenever I say NAD, I think of a dehydrogenase. And as I told you that the dehydrogenases are named according to the substrate. So this one becomes alpha ketoglutarate dehydrogenase. Alpha ketoglutarate dehydrogenase enzyme, with incorporation of a coenzyme A forming succinyl-CoA. So we produce also, there are 2 molecules with loss of carbon dioxide. Then the following one is so precious because it's called the substrate level phosphorylation, whereby this succinyl-CoA is a higher energy compound, and being a higher energy compound, if we have GDP, it donates a phosphate group to GDP to form GTP, guanosine diphosphate. We add the phosphate in organic to form guanosine triphosphate, and this guanosine triphosphate is a higher energy compound. It donates its phosphate to ADP, and we form 2 ATPs. Because this is also 2, this is also 2. We form 2 at a substrate level. This is at a substrate. So this is the only substrate level phosphorylation in Krebs cycle. This is substrate level phosphorylation. As I told you, that substrate level phosphorylation, the higher energy compound donates a phosphate to ADP to form ATP directly at a substrate level without going into electron transport chain. So in Krebs cycle, we see 2 ATPs being produced at a substrate level. And here we form succinate, and this reaction is catalyzed by an enzyme known as succinate thiokinase. So succinate thiokinase is the one that catalyzes this reaction to form succinate. And this succinate, which is formed, is still a 4-carbon sugar. It is converted to fumarate, which is also a 4-carbon sugar. And because we are going to form fumarate, which begins with capital F, I no longer think of the NAD, but I think of a FAD, because it also begins with F. So because we have forming fumarate, which begins with F, I think of FAD. But when I have FAD, it is reduced to FADH, H2. 2 molecules, 2 molecules. And after forming FAD, the enzyme is still a dehydrogenase and is named according to the substrate. So it is succinate dehydrogenase enzyme. So succinate dehydrogenase enzyme is the one that is catalyzing the oxidation of succinate to fumarate with the reduction of fad. And after forming fumarate, which is still a 4-carbon sugar in presence of succinate dehydrogenase enzyme, we see the conversion of fumarate to malate. And because this is fumarate, the enzyme is known as fumarase. The enzyme is fumarase, whereby fumarase enzyme, it catalyzes the hydrolysis reaction because it involves addition of water. So when we have fumarate and we add the water molecule, we are able to form malate. And this malate is also a 4-carbon sugar compound. It's a 4-carbon sugar compound. So malate meaning there is no decarboxylation. So this malate, which is formed and is a 4-carbon sugar, it can also be oxidized. Because we remember in the mitochondria we have a printer of oxygen. These are always oxidation reactions, but this is a hydrolysis reaction. So malate is oxidized to oxaloacetate. In the presence of malate, dehydrogenase, and whenever I say dehydrogenase, this one, I see NAD plus being reduced to NADH. In the presence of malate, dehydrogenase enzyme, we form oxaloacetate. And this oxaloacetate formed combines with more molecules of acetyl-CoA to form citrate, and the cycle continues like that. So this is how Krebs cycle occurs. So we have seen fluoroacetate being inhibited by inhibiting aconitase. It can also inhibit this enzyme fumarase. These are the reactions. So after seeing how it occurs, we now need to know why glycolysis in our body. Why do we need glycolysis in our body? So we are looking at the significance. And the major significance of glycolysis, the major significance of Krebs cycle, This Krebs cycle is to provide energy. That is in the form of ATP. Then it also provides water and carbon dioxide. This is the major significance of Krebs cycle. So we want to look at the accountability. And we want to see how many ATPs are produced by Krebs cycle. Let me begin with 1 molecule of acetyl-CoA. If I have 1 molecule of acetyl-CoA fed in Krebs cycle, I see 1 molecule. The first thing it produces is carbon dioxide, it produces NADH, produces FAD, H2, and produces ATP at substrate level. And 1 molecule of acetyl-CoA produces 1 carbon dioxide the second. So those are 2 molecules of carbon dioxide. Then 1 molecule of acetyl-CoA produces 1 NAD, second, and the third. The third is here. So those are 3. It produces 3 NAD, H. Then FAD H, it is only 1, which occurs here. That is for 1 molecule of acetyl-CoA. Produces 1 FAD H2. Then ATP at substrate level, 1 molecule of acetyl-CoA produces 1 ATP. And this one gives a total that the 1 molecule of NAD, when it is entered into electron transport chain, 1 molecule of NAD produces 3 molecules of ATP. But book says 2.5, but we always round off to 3. So we get 3 molecules of NAD times 3 molecules of ATP, forming 9 ATPs. Then 1 FAD, when it is entered in electron transport chain, it produces 2 ATPs. It is 1.5, but we round up to 3. So it is 1 times 2, which we get a total of 2 ATPs. Then plus the one at the substrate level. This is at substrate level where we are producing 1 molecule of ATP. And this makes a total of 12 ATPs. So 1 molecule of acetyl, or 1 cycle of Krebs, using 1 molecule of acetyl-CoA, it produces a total of 12 ATPs. So produce 12 ATPs for 1 molecule. However, if there are 2 molecules, of acetyl-CoA, the way we know that we produce 2 molecules of acetyl-CoA enzyme A, we are going to see the carbon dioxide molecule being produced. They are going to be 4 carbon dioxide. Then for NADH, they become, we have 2 plus 2, that is 4. Then 4 plus 2, here they are also 2, we form 6 NADH. Then for FAD, H2, we are seeing 2 of them being produced at this reaction. So a 2 molecules of acetyl-CoA, or 2 cycles of Krebs cycle, produce 2 FAD. And as we know that 6 molecules, 1 molecule of NAD produces 3 ATP, we get 6 times 3, and we get 18 ATP. 1 molecule of FAD produces 2 molecules, 2 ATPs. So we get 2 times 2. We get 4 ATPs. Then we have also substrate level, ATP produced at substrate level. And there are also 2 ATPs at substrate level. That is for 2 molecules of acetyl-CoA. And the total we get is 24 ATPs for 2 molecules of acetyl-CoA for 2 Krebs cycle, 2 cycles. So 1 cycle we produce 12 ATPs, but for 2 cycles or 2 molecules of acetyl-CoA, we produce a total of 24 ATPs. So this is why Krebs cycle is very important in our body. Its major importance is to provide energy in form of ATP, water, and carbon dioxide. Thank you so much for watching this video until the end. Always remember to share and like the video. Thank you so much for being at Muhumuza Naphtali, medicalsciences.com, and continue because more are still coming. The next video we shall look at electron transport chain and gluconeogenesis. Thank you so much.